Did you know that every single day, our entire planet takes a deep, invisible breath? It's this massive planetary scale rhythm happening way up in our atmosphere. It's a tide, but it's not driven by the moon. It's driven by the sun. And for decades, a huge part of this rhythm was a complete mystery to scientists. But the solution? Well, that turned out to be even more surprising than the puzzle itself.
So to really get to the heart of this puzzle, we first need to understand the phenomenon itself. What exactly is this daily breath that our planet is taking?
All right, so this massive planetary scale wave is pretty much the main character of our story today. It's a fundamental force, and understanding it is the absolute key to unlocking the mystery that comes next.
Okay, so it's called the diurnal tide. Now, the first thing you need to do is get the idea of ocean tides out of your head. This isn't about the moon. This is an atmospheric tide, and it's driven entirely by the sun. Every day, the sun's heat creates this huge thermal bulge in the atmosphere, which then travels westward all the way around the globe, making a full circuit every 24 hours. It really is like a giant, invisible breath the entire planet takes, day in and day out.
A daily breath seems simple enough, right? But this is where our scientific detective story really kicks off. Because when researchers looked closely at its rhythm, they found something that just didn't add up. I mean, logically, you'd think this tide would follow a yearly cycle, wouldn't you? You'd expect it to be strongest once a year, maybe during the peak of summer, something in sync with the seasons. But the observations showed something completely different.
Yeah, instead of one predictable peak in strength each year, scientists were seeing two distinct peaks. This twice-a-year or semi-annual variation was a total puzzle for a long, long time. Why was the atmosphere's breath hitting its peak strength twice a year around the equinoxes instead of just once? And look, it wasn't for a lack of trying to solve it. For years, scientists pointed to all sorts of complex interactions with other big atmospheric waves, but none of the theories, none of the math, ever fully explained that distinct twice-a-year pattern. The real culprit had to be something else entirely.
So, to finally crack this case, scientists needed a whole new approach. They decided to build a virtual atmosphere, basically a perfect digital copy of Earth's climate, where they could isolate and test different forces. They were going to put the main suspects on trial. They used this incredibly powerful tool called the Canadian Middle Atmosphere Model, or CMAM. The best way to think of it is like the perfect atmospheric laboratory. I mean, think about it. In the real world, you can't just, turn off the wind or dial down the sun to see what happens. But in a model like this, you can run those impossible experiments. And in this digital lab, they focused on two main suspects. First up, you've got tidal heating. That's the direct warming from the sun that actually creates the tide. And suspect number two, the zonal mean winds. These are the huge, steady east-west wind patterns that flow way up high in the mesosphere. The big question was, which one was causing the trouble? So what happened when they ran the simulations? Well, the investigation led to a stunning breakthrough. It turns out the primary driver of this whole semi-annual puzzle was the suspect that many people had kind of discounted before. Okay, this right here is the crucial finding. The model showed that the sun's heating only really affected the tide's strength, its amplitude, or how big the wave gets. But it was the winds. The winds were the key. They influenced not only the tide's strength, but also its timing, its phase, or when the wave peaks. That dual influence was the smoking gun. And this really shows you that aha moment. The original paper just states it directly. Discovering just how sensitive the tide was to these background winds, that was the big new finding. It literally changed how scientists understood the whole dynamic. So, okay, we've identified our culprit, the zonal winds. But that just leads to a deeper question, right? How exactly does a global wind pattern create a twice-a-year rhythm? Well, the mechanism is surprisingly cool. The key to the whole thing is a phenomenon called latitudinal wind shear, and the analogy on the screen is perfect. Imagine you're cruising down the highway and the lane right next to you is suddenly moving 100 miles an hour faster or slower than you are. That sharp difference in speed creates a ton of force and turbulence. The exact same thing happens in the atmosphere between different latitudes. And here's how it all fits together. During summer in one hemisphere, let's say the northern, these really strong easterly jet streams form way up in the mesosphere. And at their edges, they have this incredibly powerful latitudinal shear. This shear acts like a massive brake on that daily tide, weakening it a lot. So that happens once during the northern summer. Then, 6 months later, the exact same thing happens all over again during summer in the southern hemisphere. And that's it. That's the solution. You have one annual breaking event in the north and another annual breaking event in the south. When you look at the planet as a whole, these two separate annual events combine to create one single global semi-annual rhythm. The tide is strong around the equinoxes when the shears are weak, and it's weak during the solstices when the shear in one hemisphere is at its peak. Boom, puzzle solved. So solving an atmospheric puzzle is definitely fascinating. But what are the broader implications? Why does understanding this hidden rhythm actually matter in the real world? Okay, the theory that came out of the model was elegant. It perfectly explained the pattern. But this is where the story takes a really interesting turn, because there's always one final crucial test in science. Does your theory hold up when you use real-world data, not just the data generated inside your own model? The results were, well, they were shocking. When the model ran with its own wind data, it perfectly reproduced the semi-annual tide, just like in reality. But when scientists plugged in two of the leading real-world wind data sets we have, from satellites and radar, the model failed. With one data set, the pattern was completely gone. With the other, it was way too weak. The implication of this was profound. It wasn't that the model was wrong. It suggested our observations were incomplete. The model's success with its own data strongly suggested that our real-world data sets were simply missing the crucial, super intense wind shears that were driving the whole process. The study itself pointed to possible deficiencies in how we were measuring our own planet. And this, right here, is the ultimate takeaway. This entire investigation just highlights how deeply our understanding of the global climate depends on getting accurate, high-resolution measurements, especially of wind. Without them, even our very best models can't give us the full picture. It just leaves you with this final, fascinating thought, doesn't it? This was a case where a theoretical model became so good, so accurate, that it could actually reveal flaws in our direct observations of the Earth. It really makes you wonder, what other fundamental rhythms and forces are we not yet seeing clearly? What else about our own planet are we still missing?